My name is Kyle Hecker, and this is portfolio number 1 for Fluids 307. The first concept question is, what is a metacentric height, and if a center of buoyancy and a center of gravity move away from each other and a common axis, creating a new metacenter, what happens? So the answer to this is, first, a metacentric height is the distance between the center of gravity and the metacenter. So after we understand that, we can relate. The second part is what happens is, if a new metacenter is created, the object will flip over. As the center of buoyancy and the center of gravity move away, the object will flip over and is not balanced anymore. The first calculation question is, what is the pressure in a mercury manometer as shown in the figure below? And this is not just purely a mercury manometer. As we can see, it has air, oil, and mercury in it. So there's two loops, and there's two different fluids on the loop, so we have to account for the differences with that. But first, we have to do our knowns, which is we know there's a gauge pressure of 300 kPa, and we have to find our absolute pressure. We don't really have any assumptions, as this is a manometer, so there's not much to assume, as it's usually pretty straightforward. The properties we have are the density of oil, which is 790 kilograms per meter cubed, and the density of mercury, which is 13,600 kilograms per meter cubed. So in order to solve it, we do our absolute pressure, which is our gauge plus our atmospheric. And then our atmospheric is negative rho GH of the oil because we're going down this way, but then plus the mercury as we, the oil as we go up, and the mercury as we go down. So we subtract the oil, add the mercury, and then we add the gauge pressure plus each one of these divided by 1,000 to get them into the correct units, and we end up with a pressure of 802.6 kPa. The second concept question was, other than being able to simplify problems, what else can be said about a control volume? So control volume is many things that can help simplify problems and make questions easier to understand. So a control volume also should have its have its control surface oriented normal to the flow, and that's a couple things that control volume is able to do. The second calculation question was, a propeller plane is being tested in a wind tunnel with wind at 150 meters per second, and the diameter of the blades are 2.5 meters. What is the mechanical energy of the plane, and how much power is the engine outputting? And then we're told to assume a density of air is 1.2 kilograms per meter cubed. So we go to our knowns, which we write down where 150 meters per second and 2.5 meters for a diameter. We're trying to find mechanical energy and an engine output power. We are assuming a pressure of 0 and a height of 0. So in order to simplify our simplified Bernoulli's, and then our property is 1.2 kilograms per meter cubed. So to solve it, we go to our Bernoulli's, and we're able to just knock out the pressure and the height terms, and then solve for mechanical energy, which turned out to be 11.25 kilojoules per kilogram. Then we have to solve for the power output. So we use our rho equals mv and our v equals av equations. We get a volumetric flow rate, and we get a mass flow rate from that, and then we're able to use the mass flow rate times this mechanical energy output, and that is able to give us an answer in kilowatts. The third question, the concept question, was, what is the difference for the equation of mass conservation when applied to a moving or deforming volume? So the mass conservation equation is rho times volumetric flow rate. The first one is equal to the second one, or you can expand it and do rho times velocity times area, which is the same as volumetric flow rate. The answer to this question is, the absolute velocity is replaced by the fluid velocity relative to the control surface. So that is how this question is answered. The third calculation question is, an enclosed tank with 5 meters of water in it has a gap at the top with a gauge pressure of 709 kPa. The tank has a spout that ejects the water. If the tank was placed below sea level and held constant at 10 atm, how high could this spout shoot water if it didn't have to displace the ocean water? So here's a little picture describing a little bit what's going on, and we can assume there's ocean just above this. So what we do know is there's an atmospheric pressure of 10 atm, a gauge pressure of 709, and a height of the water is 5 meters. We're trying to find the height that the water could be ejected. If we assume, we can neglect water resistance, and we also have to assume volume or velocity is 0 and z2 is 0. The properties we have are the density of water, which is 1,000 kilograms per meter cubed, and gravity, which is 9.81 meters per second squared. So we go to the Bernoulli's equation, knock out both velocity terms and the second z term, then solve for P2. The big assumption in this one is that because the atmospheric pressure is acting on all systems the same, it can be neglected. So if this problem was done adding atmospheric pressure and then subtracting it later, it would give the same answer as if it was just neglected. So we can just assume it's 0, and then we can solve this equation by plugging in our values, and then we have to once again divide to get our height, which could eject the water 77.3 meters if there was no resistance from the ocean. Finally, concept question number 4. What is a radial flow device, and which equations can be used to help analyze it? So the answer to this was a radial flow device is a fan or a centrifugal pump involved in the flow in the radial direction normal to the axis of rotation. And also the equations that can help us analyze the radial flow device are angular momentum and the conservation of mass equations. Then the last calculation question. Water is being ejected from a line at 39 meters cubed per second with a diameter of 55 centimeters. Before it reaches the end, however, there is a vertical opening of 5 centimeters for a little water to escape at the same mass flow rate as this. What is the force in the x and y direction as well as the total force? So we can look at our picture here. There's a flow rate coming in at 39 meters cubed per second, and it's ejected here and here at the same flow rate. And then what is the total forces from this little picture? So our known is x diameter is 0.55 meters, and the y diameter is 0.05 meters, and the volumetric flow rate is 39. We're looking for the fx, fy, and then the total f. We have to assume we have a correct or a friction factor or a correct beta factor of 1 with a density of 1,000, and that's also a property. So we go to solve it. We have to get our x and y velocities, so rearrange the volumetric flow rate equation, and we get these two numerical values as our x and y velocities respectively. Then we go up here to get a mass flow rate, rearranging our density equation, and we can get a mass flow rate. Then we start with our x directed force. In minus out plus gen equals accumulation. Beta is 1, so we can ignore it. And then solving for fx gives 6,402 kilonewtons. Then solving for fy, and the exact same thing. We get a fy of 7.75 times 10 to the 5th kilonewtons. So then adding those together to get the total force, we have to do the magnitude. So squared each one added to each other, square rooted, and we get 7.75 times 10 to the 5th kilowatts. Finally, the appendix of what was changed from the original IQEs. Question 1, a new concept question and calculation question were formed based on the feedback from the original turn-in. The concept question originally was a true-false question, so that was changed to something a little more in-depth. And the calculation question was a MC delta T question, which is not purely fluid, so that was changed in order to a little more represent what fluids is like. Question 2 was the concept question was changed, and a calculation question was reformatted to be more accurate. The concept question was originally a multiple choice, so that was changed to be more in-depth and accurate of fluids, and the calculation question was reformatted into the correct KFAPS format. Question 3, the concept question was left the same, that was not changed, but the calculation question was adjusted as the pressure didn't affect the system. As discussed, whether you added or didn't add the pressure didn't affect the outcome of the problem for this question, calculation question 3. And then question 4, the concept question was again left the same, and the calculation question was adjusted so the flow rate was more understandable. In the original problem, it was not understood whether the flow rate was coming out of both holes, so it was more written in depth as to understand that the flow rate came out of the vertical and the horizontal ejections.